Today's webinar is called Soil Detective Work, Reading a Soil Profile. This session will provide you with an approach to using visual interpretation skills to identify soil horizons and parent materials in a variety of soil profiles. Reading these soil profiles will help provide an understanding of soil properties and soil classification. Soil monoliths at the Great Lakes Forestry Centre will be used for this webinar. For this webinar, we welcome back Paul Hazlett. Paul is a forest soil scientist with Natural Resources Canada, specifically the Canadian Forest Services and Sault Ste. Marie. His research focuses on the impacts of atmospheric deposition and forest management practices on nutrient cycling and forest soil sustainability. So without further ado, I'd like to welcome Paul. Paul, whenever you're ready.
Great, Diana, thanks. I'll share my screen here with everybody and we'll get started. Just like to say thanks so much for Forest Ontario for inviting me back for this second webinar. I did one in January, and thanks to you folks that have tuned in live to hear it. I guess what I'm going to try and do today is put together, as Diana said, a presentation on soil detective work, reading a soil profile that would be useful to people that are tuned in today to hear about it, but also to play back at some point as it is being recorded. And thinking that it's useful both to first-time Envirothon students, students that have been involved in Envirothon for a few years, and also mentors and resource people that might be looking for some teaching resources and ideas to use down the road in their mentoring of students that are competing in Envirothon. So we'll move on. What I'm going to talk about today, I'm going to start talking about a little bit about the importance of soil, why we would even be classifying or sampling soils in the first place, what the reasons are behind that. Go through the soil forming factors, and then talk a little bit about some of the steps we can take to reading a soil profile, and then trying to do that hands-on, actually looking at some monoliths, which are soil profiles that have been extracted from the field and mounted as teaching tools to do that. And then we'll finish up with a question period. So just to start off with, just to focus on the importance of soil, I like to think of soil as an ecological unit, and it really plays an important role just about in areas that touch all aspects of our lives. So starting from the upper left of this slide, you can see that we think of soil as an important medium for plant growth. That's very straightforward, showing a tree here, but it could also be applied for everything that we grow and eat. And one of my things I often do with Envirothon students is ask them to tell me what they had in their breakfast or lunch today and trace it back to the soil. And so far, nobody's been able to come up with anything that they eat that didn't originate from the soil in the first place. Another important function of soil is a recycling system for our nutrients and organic waste. That can be as easy as looking at landfilling and where we put our garbage. Then we can also think of soil as a place where there's much biodiversity. So in this case, it's showing a picture of a worm coming out, but really soil is habitat for many different types of microorganisms up to macroorganisms that all depend on the soil habitat for their life and form a soil food web that feeds upper organisms as well based on those lower trophic levels. From a very practical point of view, we think of soil as something we build on, and obviously we have to understand something about those materials before we put roads or buildings on them. So soil is important in that way. And then the final one in this slide shows soil as a system for water purification. So thinking about the fact that much of the water that we get for drinking water comes from either surface water or groundwater. And of course, the source of that surface and groundwater is soil. So the water that comes through soil ends up being the water we drink eventually. So, I mean, this is a very quick, I could talk all day about how important soil is and why it's really the foundation and probably an underappreciated natural resource that we have but this gives the upper level description of that. So that leads us into the idea that if soil is so important, we have to have some understanding, some ability to classify soils so we can determine, how they exist within the ecosystem and how we might use those soils in any practical application. And that brings us down to this idea of soil classification. So in a nutshell, what soil classification is, like any other classification system, we're trying to group together similar soils. So soils that have the same morphology, the same properties, the same processes going on. And then the classification should also separate meaningful differences between different soil types. The photo on the right here, I'm actually in the middle of the photo in the blue shirt and the green hat, is a photo taken several years ago at a soils conference. And it's always interesting to see an open soil pit with lots of soils people on a bus just rushing to get in that pit. But what you see going on here is lots of debate about the classification of this soil, how this soil formed. It's always an exciting time with a bunch of soil nerds getting out to look at profiles like this. So the one thing that I want to impress on everybody today is that while we do have this soil classification, the real importance of the classification is that it really determines the suitability, the limitations, and the response of the soils to agriculture, forestry, buildings, recreation, waste management, all those things I mentioned on the previous slide, but all other uses of soil. So the classification system and establishing that is really the foundation for how we are able to utilize soil in these different ways and realize the limitations of using these soils for some things and not for others. So that leads us into this idea of the soil forming factors. And this may be a review, like I say, for some Envirothon students. This is kind of a basic thing that we think about with soils, but it is important to keep reminding ourselves of these soil forming factors as we look at soil profiles in the field or the monoliths, as I'm going to show later today. So the real point about the soil forming factors, or the real question is, why do soil profiles look different from one location to another? And the short answer is it's because of different soil forming factors. So soil formation is a function, and that's what you see here, the S equals F, is a function of climate, organisms, parent materials, relief, and time. So these five elements are the soil forming factors. And the differences in these factors from place to place determine what a soil is going to look like, what its properties are going to be, what processes are going on in it when you go from one location to another. So let's just talk about a couple of points of them quickly. The first one was climate. And this particular graphic shows changes in climate, that is mean annual precipitation on the y-axis, mean annual temperature on the y-axis, mean annual precipitation on the x-axis, and how changes in these two important variables of climate result in different vegetation types. So you see with very low annual precipitation and very high temperatures, we end up with deserts. When we still have high temperatures, but we increase the mean annual precipitation, we end up with tropical forests. So the importance of this to soils is that depending on this climate, you get different vegetation types, and these different vegetation types provide different types and amounts of organic matter to the soil surface. So, and again, in a simple example, if we took a grassland soil, when the grasses die and fall over, they're inputting different grass organic matter into the soil. When you look at a coniferous forest, a totally different litter type in terms of needles is coming off those trees and being inputted into the soil. And of course, that organic matter then decomposes and moves through the soil. and creates a different profile depending on that vegetation type. So the climate is very linked to the vegetation, and the vegetation is very linked to the climate, and that then influences how the soil will look and develop at a particular site. So vegetation is one kind of organisms, but we have lots of other organisms as well. In this case, I'm showing one of the most viewed, I guess, organism within soil, and that's an earthworm. So this is just one example of an organism, a soil organism, that through its digestion of soil particles is moving organic matter and soil throughout the soil profile, and because of that, changing the way that the profile develops. And as I said, the earthworm is only one example. There are many other organisms in soil, and they differ from place to place. Again, linked to climate as well, what organisms will be in one site or another. And again, they can change how any particular soil looks at any particular site. So soil is a function of organisms. The third element, or the third soil forming factor in the equation, was parent material. And when we think about parent material, what we're talking about is the material that the soil developed in, the material that was either deposited by a glacier or by a river, or just bedrock weathering that the soil actually forms in. And so I've shown a few photos of parent material here, different clays, fine sands, glacial till with lots of different boulders and sizes of fragments in it. And if you could, I guess the best example we can use in Ontario is the fact that Ontario was at one time totally covered by glaciers. So any particular soil profile has developed in the material that was moved around, laid down by the glacier, and now 10,000 years later has a profile development in it because of soil forming factors working on that parent material. And parent materials can be very different in their chemical makeup as well as their physical makeup. So another good example here that I use to point out to students is that in southern Ontario, we have parent material that has very high pH. That's basic soil material. So we have a lot of limestone bedrock in southern Ontario, and therefore the soils that developed in southern Ontario are quite alkaline and have high pHs because of that parent material that they developed in. When you move into the northern part of the province, where more of the bedrock is granitic material, which is acidic, the soils that develop there are acidic soils. So again, an example of parent material having an impact on soils and the soil development because of its chemical characteristics. We move on to relief as a soil forming factor. And what this diagram is showing is 4 different soil pits from left to right that go from well-drained, moderately well-drained, poorly drained to very poorly drained conditions. And the significance of this is that water moves up into the soil profile and saturates the soil for different periods of time throughout a year, depending on where you are on this landscape, this katina, as we call it. So the soil, even though these soils are quite close together, or could be quite close together and could experience the same climate, the same parent material, the drainage condition of each site, the relief, will alter the development of the soil in many different ways by saturating it, by excluding organisms that need air to live. So relief is an important soil forming factor as well. So here's the equation again, just a reminder. So soil formation is a function of climate, organisms, parent materials, and relief. And the last soil forming factor that I haven't mentioned yet is the T, and that's for time. So a soil will look different depending on the amount of time that the other soil forming factors have had to work on that soil. So again, using Ontario as an example, we're generally regarded to have quite young soils in this part of the world. Because of the glacier, the soils are 10,000 years old only. Other areas that haven't had glaciation could have soils that are hundreds of thousands of years old, that have had that amount of time to develop with these other soil forming factors. Okay, so we move on to there, and I'll draw in the link of the soil forming factors, but now just some ideas about reading a soil profile. And it's interesting to be doing this on the computer. My preferred option would be in the field, like these two students are, to look at a soil profile and use their visual skills to do some of the things we're going to try and do here on the computer and in the laboratory. The first thing to know is that reading a soil profile really involves some visual interpretation skills. So the first thing I always ask students when I put them in a soil pit is I say, what do you see? What do you actually see? And that's getting at these questions, first of all, as identifying the parent material that's on the site and identifying the soil horizons. And in the end, in some situations, coming up with what we call a diagnostic horizon, which would be a horizon that would be specific to a soil at any particular site and would enable us to classify it into a certain soil order. And again, that soil order would represent a certain situation in terms of horizon development and chemical properties and physical properties within that, and biological properties within that soil. But one thing to keep in mind as we're doing this, we can use our visual interpretive skills in the pit, but it's also important to keep those in the context of the soil forming factors at the site. So what do I mean by that? Well, let's take a look at this picture, and you can tell that the students aren't standing in any water. So this particular profile is upslope on a hill. So right away, when we're thinking about this profile and interpreting what's going on in the profile, we can assume this is a fairly well-drained soil that doesn't have a water table up into the profile at this time of the year anyways. So that's one example of how we should keep those soil forming factors, climate, organisms, parent material, and relief in mind when we're trying to interpret and read a soil profile. And then once we've done this, we've identified the parent material and we've identified the horizons and the diagnostic horizons, a logical next step for us is to actually classify the soil, and that soil classification relates back to the specific soil properties at that site. Okay, so here's some first steps that we could do. Pretend we're in a soil pit now. We're going to go to a monolith in a minute. The first thing is to identify the parent material. And here's the steps how we can do that. So first of all, the parent material is at the bottom of the soil pit. Over time, or let's go back and we'll use an example again of some glacial material. When the glacier left a particular site, the soil looked the same from top to bottom. So the material, the parent material that was laid down looks the same from the top to the bottom of the soil pit. But over time, as an example again, over the last 10,000 years, the soil forming factors have changed that parent material. And what that means is that the surface of the soil has been changed. If we dig far enough to the bottom of the soil pit, we can find the parent material unaltered from those soil formation processes. So if we're going to identify the parent material, then the first thing we have to do is look at the bottom of the soil pit, because that's the area of the pit that's unaltered by those soil formation processes. So then here's the questions we ask. Are there coarse fragments in that parent material? How big are they? And when I'm talking about coarse fragments here, I'm talking about fragments that are greater than 2 millimeters in size, in diameter. So we would consider everything less than 2 millimeters to be soil, or fine earth, everything greater than 2 millimeters to be coarse fragments. How big are they? Are the coarse fragments rounded or angular? Is the soil material mineral or organic material? So is it made up of sand, silt, and clay? Or is it really decomposed plant material in some form? And then when we're talking about the mineral material, is it sandy, coarse textured material? Or is it clay, fine textured material? Again, that will tell us something about the type of parent material that's been laid down on the site that the soil profile has developed in. And then lastly, are there layers or bands of materials? So not thinking about soil horizons strictly in this case, but are there bands of materials of different texture or mineral or organic that show up through the soil profile? So those are some easy questions to ask. So what are some typical parent materials and what would they look like? And I've listed some examples here. I'll go through them quickly, but you have them for your reference. So glacial till is material that's created by melting ice. So if you can picture the glacier carrying along all kinds of unsorted materials, a mixture of boulders right down to clay-sized particles, and the ice melts, and that's deposited on the landscape. So when we dig a soil pit in that, we would find all this unsorted material of all different sizes. In addition, a lot of the coarse fragments, the rocks that are in the profile, would all be angular, and there's no layering in a glacial till deposit. We move on to a fluvial deposit or a glacial fluvial deposit created by a glacial river or a river. And in this case, the water sorts the materials and it layers it. And predominantly you have sands and gravels in these kind of parent materials because the finer materials are carried away in the water. The water moves fast enough that it carries away the fine materials. And in addition to this, you'd find that the coarse fragments are rounded. And again, that's due to the rounding of the coarse fragments by water, the weathering by water. And you can see this just today if you walk down into a local river or creek where you might live, where there are rounded stones throughout that river or stream, and that's because of this action of water. The third type of deposit I'm going to mention here is called a lacustrine deposit or a glacial lacustrine, and lacustrine is just a fancy word for lake. So these kind of deposits are lake bottom deposits, and they're quite different from the previous two because now they are dominated by the fine textured soil materials, mineral materials, so the silts and the clays. And again, you don't have any coarse fragments in these lacustrine deposits. So if you come across a deposit with these fine materials and no coarse fragments, then it's a lacustrine deposit. And then the last one I'm going to cite here are organic parent materials. So these would be non-mineral, so no sand, silt, and clay deposits. They're usually occurring in cool, wet environments. So in parts of northern Canada, the Hudson Bay lowlands is a really good example of a large area of these kind of organic parent materials. And what those materials are just organic materials in different stages of decomposition. So some that have been on the landscape for quite a long period of time and are highly decomposed, and others that are freshly deposited that are not decomposed to the same extent. So there's the parent materials. Now, step 2, we move into identifying the soil horizons, and a few steps here again. So again, I like to point out to students, we're going to examine the face of a soil pit. So we dug a soil pit. That face we call the soil profile. And the different layers that we have are called soil horizons. And the way we distinguish these layers, the simplest property we use is color, but there also can be differences in texture and soil structure that help us distinguish one horizon from another. And again, a key to this step is examining those horizons, keeping in mind the soil forming factors. So if you are in a sugar maple forest, then you would expect to see some organic horizons on top of the soil surface that are created because of the depositing of sugar maple litter every fall. So you can use the soil forming processes to help inform your decision about identifying the horizons. That's what I'm trying to get at here. So then again, some questions. Is the horizon mineral or organic? How thick is the horizon? What's the color? What's the structure of the horizon? Are there mottles or glaying present? Now here's a couple of fancy words that I don't know if anybody or everybody has heard of, but mottles are flecks of iron oxidation that occur in soils that have a fluctuating water table. So there may not be water in a particular soil profile today, but if you see these mottles, you can say that there has been water in that part of the profile at one time or another in the year. And glaying is where you have a part of the soil profile that is totally saturated water for most of the year. So this would be below the water table. So again, these are clues to help you identify the soil profile. And again, in this case, you might expect these to be occurring in lower slope positions. So again, thinking back to the soil forming factor of relief, that plays a great role in terms of determining whether there's mottles or glaying present. Where are the roots in the profile? And in the end, coming up with what is the diagnostic soil horizon for the profile. So which horizon is the unique one that separates this profile and determines what soil order it is going to be part of. Now, it's really impossible in 45 minutes or so, the time that I have today, to go into the details of determining horizons and all the different horizons that could be out there. So what I've decided to do is talk about two aspects of it. One is the so-called master soil horizons. So this is like Soil Horizons 101 for Envirothon students to get them understanding. And I'm going to go into a minute in more detail about some of the different diagnostics horizons, which just means more specific classification of the master horizons. But let's take a look at this diagram, and we'll start off at the soil surface on the right-hand side. So we have horizons L, F, H, and HI. These are organic soil horizons that occur in upland slope positions. So the L stands for litter, the F for fermentation, and the H for the popular humus. Please don't call it hummus, although that's good too. And the HI is a humus layer with some mineral material mixed into it as well. So these are organic horizons. That means they have greater than 30% organic matter, and they're occurring at a site where you've got organic material coming into the site and starting to decompose from some form of vegetation that's on the site. So the litter is the least decomposed, the fermentation intermediate, and the humus the most decomposed of these horizons. So again, they're organic horizons on an upland site. The O horizon underneath that shows OF, OM, OH, it's not actually shown in this diagram, but those are the organic horizons that we would have in a purely organic soil, where we have organic parent materials that I talked about, where these are wetland areas, peatland soils, where we have these three different horizons. So again, it differentiates from the upland soil to the wetland soil. And the OF stands for fibric, the OM for mesic, and the OH for humic. And again, like the LFH, this represents a gradient of decomposition from the OF through to the OH. So more decomposition once you get deeper into those organic soil horizons with the OH. So those are the organic horizons. Below that, we have the master mineral soil horizons. So again, these are mineral soils, highly composed of sand, silt, and clay, and less than 30% organic matter within these horizons. And again, I like to say to students, master soil horizons, mineral soil horizons are as simple as ABC, because they are ABC. So we think of A as being the surface soil, B as being the subsurface soil, and then the C horizon, we're actually getting down into our unweathered parent material. So that's what I was talking before when I was talking about parent materials. We look at the bottom of the profile, and that's where the unaltered material is. That's our parent material. That also is classified as the C horizons. So those are the master soil horizons. I'm not going to go through this slide in detail, but I wanted to show for further reference if people want to look. These are the diagnostic soil horizons that we identify for the different soil orders that we have within Canada. So within our classification system in Canada, we have 10 different soil orders that are showed on the left side of this table. And what makes any particular soil fall into any one of these orders is the presence of this diagnostic horizon that's shown in the second column. So, and then on the right-hand side, there's some comments about what this diagnostic horizon looks like. And again, this would be characteristic of just that type of order to fit it into that classification order. So just as an example of the first one, Chernozemic soils are grassland soils in the Canadian prairies, and their diagnostic horizon is an A horizon with a subscript H, and the H stands for humus in this case. And what these particular soils have is a dark colored organic matter enriched surface horizon due to the litter fall of grasses each year that have built up this organic matter layer within that A horizon. And again, I'm not going to go through all of them here, but you can see there are specific comments, specific descriptions of each of these diagnostic horizons that fit them into the classification system. Okay, so I'm going to take a few minutes here and just provide an overview for 4 monoliths that I've moved into our lab here, and we'll take a look at identifying the parent material and looking at some differences in parent material between these monoliths and also the soil horizons. Before I do that, I just want to let you know that the monoliths that I'm going to show here today, we have a small collection of them here at the Great Lakes Forestry Centre in Sault Ste. Marie, out in the wall in the hallway here. So I brought them into the lab, but they're also available on the internet at this web link. So if you want to use these monoliths for any teaching, you can access them at that website shown there. Okay, I'm going to stop sharing the screen here for a moment, and we'll take a look at a couple of these monoliths, and I'll try and provide just a short dialogue on these monoliths. So I think I'm off, hopefully I'm off screen now. Diana, can you hear me? I'm not sharing anymore.
Yep, I can see you. That's fine.
Okay, I'm going to move the camera here, and we'll see how this works.
Okay.
So here's the first monolith I want to show you. It's going to be interesting. I'm going from the surface, I'm going to move from the surface down to the bottom of each one of these and sort of zoom in and out a little bit. So this first one has an LFH horizon. So it's an upland forest soil. And again, you can see the buildup at this profile of maybe about 8 centimeters of LFH. And you can also see the gradient of decomposition from the top of the LFH to the bottom of it, where we've got some humus present. I'm going to zoom down now to the C horizon, or the 2C horizon in this case. Again, just to sort of work on the idea of the parent material at this site. So you can see throughout the C horizon, there's no coarse fragments whatsoever. And you can also see, you can actually pick out the size of the particles in this case. I'm not sure you can see that exactly on the camera, but I can here. And I can tell you that it's a fine sand material that's down in this C horizon. So based on the fact that there's no coarse fragments, and we've got this fine, and based on the fact that I know where this exactly came from because I dug this profile, this is a glacial fluvial deposit. So a glacial deposit of sands predominantly that developed because of a glacial river moving this material along and depositing it. And now this profile has developed. Okay, I'm going to move to profile number 2. And in this case, I'm going to focus, again, I know this is difficult because I'm only showing part of the profile here at the different stages. But what I want to show here is now I'm in the C horizon of the second profile. And you can see that throughout this C horizon, there's a number of coarse fragments. And at closer examination, you can see that they're all different sizes of coarse fragments. And I can also see some sand, and there's some finer material in this C horizon as well. in addition to that, the coarse fragments here all seem to be quite angular in shape. I can zoom in on a few here to see. They're not rounded at all. So if you're following along, and I'm not going to take any questions right now, obviously, but if you're guessing, you've probably guessed that this is a profile that's developed in a glacial till. Angular coarse fragments of all different sizes throughout the profile. Okay. I'm going to move up in this profile again and just look at the horizonation in it as well. So we've got some from the C horizon, we've got a B horizon, and we move into an AHE horizon here. So an an A horizon that's been eluviated, has had materials, iron and aluminum, moved out of it to give it this bleach color. And on top, like the first profile, we've also got a thinner but still present LFH horizon. This profile actually came from the Turkey Lake watershed. It's a research site that we work on north of Sault Ste. Marie that has a 95% sugar maple forest. So this is sugar maple LFH horizon on top. Okay, I'm going to move. I've got two more profiles to go here, and then we'll be done. Moving on to profile number 3, we're now down at the bottom of this profile, and you can see right away that in this case, the material is not mineral material. It's organic material. So this is an organic parent material. There's no coarse fragments at all, and you can actually see the organic matter fragments. There's no sand, silt, or clay in this profile at all. And again, I know where this came from because I took this sample, but this was from a wetland area up north of Cochrane, Ontario, that was in a permanently saturated area where all different types of organic matter, sedges, grasses had come down and could not decompose because it was wet all the time. And as I move up through the profile, you'll see that I go from very well decomposed to less well decomposed surface at the top of this organic profile. So you can see that it's organic matter that has had very low decomposition at the top, all the way down again to the bottom here that's very well decomposed. And I've got one more profile. This is kind of an interesting one that I want to show. I'll start again looking at the parent material. It's very similar and comes to a site quite close to the first profile I showed. No coarse fragments at all in the C horizon in the parent material. Fine textured sand. So this is also a glacial fluvial deposit. What's really interesting about this profile was I'm going to move up from the parent material now into the B horizon. You'll see some color differences, and up again to that AE horizon, that bleached A horizon that's had iron and aluminum move down. But you notice in this case, there's really no LFH horizon on the top of this profile. There is some growth of some mosses on top, but there's no LFH horizon present like there was in the first profile I showed. So again, if you're guessing at home or wherever you are, this profile I actually sampled from a site that had recently had a forest fire. So in this particular case, the LFH horizon was totally burned down to the mineral soil. It was a very hot fire. So this particular profile, because of that, has had its LFH horizon totally burned off. And at the soil surface, at the ground surface, is now the mineral soil horizon, the A horizon, with no organic horizons on top. Okay, so that's my attempt at trying to show you a few of these monoliths and some of the things we were talking about, or I was talking about, in terms of reading the soil profile, the parent material, and the soil horizons. Just got one more slide to share, and then I'll be finished. And it's really just the closing slide to say thanks very much again for allowing me to present this webinar, and here's some other resources that you can use as students and teachers and mentors of students for the Envirothon program, and my contact information is on that slide as well. So with that, I guess I turn it back over to you, Diana, to see if anybody has any questions.
Thank you, Paul. That was really good. I hope you all enjoyed that webinar about reading a soil profile. Now, I would like to go ahead with the Q&A session. I do have 2 questions for you. The first question is, how many soil layers can you see with the naked eye?
So how many soil horizons can you see with the naked eye?
Yeah.
Yeah, there's no fixed number. There can be profiles that have 6 or 8 different soil horizons. So, and again, we're talking about using some visual interpretation of color and texture and structure. So while I outline to you the master soil horizons, the A, B, and C horizons, there can be multiple A, B, and C horizons at any particular site.
Okay.
So I don't want to put a limit on it. I haven't seen one with 15, but I have seen different soil profiles that might have up to 6 or 8 different horizons.
Okay, thank you.
Yeah.
And the next question is, how does rock or fine sediment become changed into topsoil?
Yeah, so that's a good question. I sort of beat around the bush on that a little bit initially, talking about parent materials.
Okay.
But, coarser materials, rock, becomes soil through the process of weathering. So we have physical or chemical weathering that takes place where physical breakdown of rock, coarse fragments occurs, creating soil, or chemical breakdown. Different acids that are created naturally can break down rock material into smaller particles to the point where we get sand, silt, and clay.
Okay, thank you.